Before we get started, we have some problem definitions to go through. We have our design based off of in the application of fish tanks. So in large fish tanks, you need a lot of filtration to handle the livestock that you're keeping. So you would have a sump tank, you can do all the filtering, get the water down into your sump tank, have an emergency drain, which is yellow, you have a standpipe, which is orange, then you have a return pump, which drives that water back into your display tank. The issue with this traditional design is that the water is always bouncing between either the emergency drain in yellow or dropping down to the height of the standpipe. You have a little bit of control over this gate valve. But typically in these systems, the water level is always changing, so you have issues with noise, you have issues that occur with flooding. I can attest to that from personal experience myself, having owned a saltwater fish tank and flooding my bedroom and having to replace the carpeting. And with the noise factor, it's always fun waking your wife up at 2 in the morning because your fish tank's making a bunch of noise. So we set out to create a device that would regulate flow into the sump based on flow in the entire system and to solve these problems.
So let's look at the main objective. Our main goal is to design and build a device that operates mechanically and solves the problem. So our device should reduce the noise coming from vortex, and it should be easy enough to install, and it should not require regular maintenance. And finally, it replaces traditional gate valve. And ultimately, the new device should self-regulate the water flow flowing through the sump according to the water level of the overflow box. Let's move on to the planning. The time period we got to complete our project was one complete academic year. In this case, fall 2021 and spring 2022. In order to keep everything, we created a Gantt chart for each semester, which shows the task and timeline. Our plan was to do the planning and designing in the first semester and do all the prototype and simulations in the final semester. First, the problem was defined and the team was formed. So we researched on possible solutions for our problem. Initially, we had 3 alternatives, and later we introduced another alternative, which totals to 4 alternatives. Then we did a market research to find out what are the devices that are already in the market. Let's focus on the Gantt chart for spring 2023. We started creating CAD models using SolidWorks. Then we moved to calculation part to see if it is mathematically free, and also the limitations that we have. This involves laser, and the other part was moving to the prototype. This involves laser cutting, 3D printing, and laser engraving. And then lastly, the evaluation to make sure the device that we produce is fit.
So let me introduce our alternatives. The first alternative, we call it Bernoulli's principle alternative. You can see those inlets on the pipe. So by using Bernoulli's principle, we could estimate the water velocity passing through them. So when the water level in the overflow box is high, then those inlets will at a relative lower position, which could create a large velocity. And so here are 2 equations we involved. The first one is Bernoulli's principle, and second is to calculate the water flow rate passing through it. And here comes to our second alternative. We call it torsion spring gate alternative. It's controlled by a torsion spring gate. The opening size of the spring gate based on the water head. Like if the water level is high, then more weight from water could be applied on the spring gate to create a larger opening size. And if the water level is not high enough, then the opening size will be smaller or even closed. And here are two equations mainly involved in this alternative. The first one is to calculate the weight from fluid above the spring gauge. And second is the relationship between spring gauge angle, spring constant, applied force, and the created moment. And next is our third alternative, buoyancy float alternative. It's controlled by buoyant force. The plug will move up and down along with the water surface. And since the plug is a like horn-shaped plug, it has variable cross sections, and which could help us to create variable water inlet area. And also, if the water level is not high enough, the plug will seal the pipe. And you can see a tiny hole at the center of the plug. That could help us to balance the pressure inside the pipe and outside to help us to seal the pipe but not vacuum seal. And this equation is to calculate the buoyant force about the plug. And next is our last alternative, the float and gate combination alternative. This comes from an combination idea of several approaches. The purple one on top is a floating cylinder, and the green one on the bottom is the gauge inside the pipe. We connected two parts together with fishing lines. So once the water level goes up, the purple cylinder will float and lift the bottom gauge, which could allow water passing through it. And if the water level is not high enough, the cylinder will return to its initial position and the gate will be closed. So this design could help us to reduce the noise and also store some water in the pipe to save time. Like next time, if the pipe needs to be drained, it doesn't have to fill out the whole pipe. So we use modified Bernoulli's principle. It's a energy equation for fluid in the pipe. Here is the equation.
So how do we select the best design? Let me go through the selection process. There are 6 critical criteria in order to find the best design. They are operational noise, manufacturability, robustness, size, maintenance, and cost. In terms of operational noise, concept 4 performed best. So the concept 1 was easy to manufacture, but the noise was unacceptable. Concept 4 won the overall robustness. In terms of size, concept 1 was small and concept 4 was the largest. In terms of maintenance, concept 1 and 4 showed a good standing. And looking at the overall performance, concept 4 was the best performing device which fulfilled all the requirements.
So we did an analytical analysis for our prototype. And as I mentioned, we use the energy equation for flows in the pipe. And here is an expanded form for our design. We separated the whole device to 3 parts based on the different diameter, pipe diameter. And also cite the stage 1 as the overflow box water surface at stage 1 and the sump water surface at stage 2. And during the analysis, we assume 800 gallons per hour pump was applied. And actually, it's enough for a 160-gallon fish tank. In order to verify the prototype, we need to compare the required needed surface height difference. So for our device, the surface height difference is 0.6604 meters. And after calculating, in order to pass through 800 gallons per hour flow rate, we need at least 0.532 meters, which is smaller than our height difference. So it's feasible. Also, we did calculation for 900 gallons per hour as well, but with a low safety factor, but still work ideally.
So for the design of float, We perform force analysis to see if the tension is within the range to lift the gate up. Since the float was designed using a known material, we were able to calculate its volume. And also, then we verified the Burns force acting on the float can lift the bottom gate successfully.
So when considering materials and manufacturing this device, we had to research what is actually an acceptable material in aquarium systems. And it turns out that there really is not a standard for these safe materials. And it's more or less what we understand as being safe for the organisms that be in these systems. So what's safe for people is not necessarily safe for vertebrates or these animals that we're keeping. For instance, we can use copper piping. We can drink water from copper. Copper piping will certainly kill any invertebrate that you have in your system. So the standards that work for us are not the same standards that work for these very delicate creatures. So the rule of thumb is use materials that are absolutely non-toxic and not water soluble. And the materials that we use that are commonly used in this industry are acrylic, PVC, ATG, which is the 3D printing material, 2HMW, silicone, ABS, and fishing. So we did the manufacturing at laser accuracy. We used a 4-axis laser cutting machine with laser engraving, and we utilized FDM 3D printing for a lot of the components. And then everything else was assembled by hand for testing. So during the testing, we utilized a 55-gallon trash can that acted as our sump and a spill container in case anything went wrong. We also had a 5-gallon bucket that represented our display tank, and we used a 400 or 740 gallon per hour pump to return water from the trash can and put it into the 5-gallon bucket. The goal is to keep the 5-gallon bucket from overflowing while varying flow. Keep the standpipe filled with water, also varying that flow, and for our device to function continuously and quietly. So at the end of quite a few tests, a lot of iterations, we were able to get a design, which is the one we passed around, that was able to run continuously for 20 hours while varying flows between 400 and 700 gallons per hour. And that limitation is not due to our device, it's actually due to the pump we had for testing.
So, looking at the code of ethics, there are 2 principles and 3 canons involved in this project. So, the principle 1, using their knowledge and skills for the enhancement of human welfare, and being honest and impartial, and serving with fidelity the public, their employers, and clients. Looking at the canon 1, engineers shall hold paramount the safety, health, and welfare of the public in the performance of their professional duties. And canon 4, engineers shall act in professional matters for each employer or client as faithful agents or trustees and shall avoid conflict of interest. And lastly, the canon 6, engineers shall act in such manner as to uphold the enhanced honor, integrity, and dignity of the profession. Let's look at the constraints.
So for our design, there are a few constraints. The first one, due to the limitation of equations, we couldn't find the relationship between prototype size and actual water flow rate right now. And also the cost goes up because most of our parts were ordered online individually. If in the future we could invest it in the production line and inventory, it could greatly reduce our cost. And for the impacts, as Burton mentioned, all materials are environmental friendly and non-toxic materials. And also, like if we could solve the emission limitation in the future, then it could be used for similar industrial water system. And also, once we have a chance to put it on the market, we believe it has potential to be a high-end product but a low price. And the last, the most realistic, important thing is our device could save people's floor, save money, save time from water overflow. And also we can save fishes' life from salinity imbalances.
The cost target for this project was to make a product that would be under $100 for a customer to purchase. See the chart here, we were actually able to get material cost for $10. That doesn't actually represent the total cost, considering we did all the manufacturing and design ourselves, but I think that's a pretty good sign, being under $10 for material costs, that we could actually make a feasible product that's something most people in that hobby could. The budget for our project was just under $300. Minimum order quantities for a lot of them too, so we just kept it from being any lower than that. Again, this is just looking at the material costs that were involved in this project, but doesn't consider things like manufacturing, design, testing. So it's safe to assume that it was probably less than $1,000. Recommendations in the future, testing with this and moving forward with it. There was leakage that was noticed around the gate that different means of production, manufacturing, be improved there. Fishing line that we used in this was also plastic, so that caused a slight delay flow in the reaction of the gate itself. Having an inelastic material in place of that fishing line would create better, stable interaction with items. And since we mentioned earlier with the testing, the limitations of the pump that we used, it would be better if we used a pump that could actually work through that entire 0 to 900 gallons per hour range instead of just 400 to 700 gallons. So in conclusion, we did prove that it's possible to make a mechanical valve that can control water height and overflow. We did have the device that's being passed around that was operating 400 and 700 gallons per hour, 20 hours straight. And it was doing that silently. So the other thing that we were concerned about, since this is going to be a product that people are going to have to be able to install themselves, is to make sure that it is easy to install. It took us less than 10 minutes to get it installed, and it is a toolless assembly, so that also makes it easier for people to maintain in the future and assemble as well.
And we'd like to acknowledge the support and efforts of our faculty advisors, Dr. J.V. Montfort, for providing continuous support throughout this project. And also our course instructor, Dr. Badi Shrestha, for providing necessary guides to be successful in this project. And also Dr. Upul Athanayaka for helping us to use his lab premises to carry out testing. And also the help we received from College of Engineering and all the faculty members who taught us during the past years, and all the people who work here, and all the facilities available in the college. Lastly, we would like to acknowledge the Laser Accuracy LLC in Grand Rapids for extraordinary support we received in terms of 3D printing, laser cutting, and engraving services for this project at no additional cost.
And here are our references used during our design and analysis. Thank you. Any questions?
Got answers.
So I think part of it actually starting my computer. Anything like this on the market? You guys research or is there the patent idea that you have?
As far as we're aware at this moment, it's a technical idea. There are some products that try to solve this, but they don't do a good job. So they do require still some monitoring. They still make noise. They're just slightly better than having a fixed gate element.
So do you plan to continue developing products? This is going to be it.
I would like to have something like this for a fish tank in my bedroom. It'd be nice.
Yeah, I mean, if you have time and money, we can keep doing it.
Like chat here. How do you do that? So we get your like input on biggest lessons learned by doing like this. And your biggest learning opportunity in this.
I would like to start. So the biggest thing I learned is the teamwork. So yeah, it was really helpful. Like each one gave different ideas, then we discussed each other and came to one conclusion and thought go ahead.
And for me, like, of course, the teamwork was great. And actually, I know nothing about fish tank before this project, and I learned everything. Like all of them are new to me. And also, like during the analysis part, I improved my skills by using all equations and like use them in a real world case. That's great for me.
Say biggest lessons learned are smallest problems can prove to be quite tricky to solve. That you need to give yourself enough time to deal with those problems that seem minute. Teamwork is really important. I did come into this bit more knowledge than my partners on this, but it was really good to get you guys caught up to speed, and you guys helped bring in a lot of really good ideas that ultimately help us solve this problem.
Give them a big round of applause.